All right, the dot product. Well, this is the first concept of multiplication between two vectors that we'll define. And we define the dot product two vectors. Well, it's denoted with a little dot, A dot B. And if A is a vector with components A1, A2, A3, and B is a vector with components B1, B2, and B3, the dot product is defined as the vector whose, actually, I made a little mistake there. It's going to be A1, B1 plus A2, B2 plus A3, B3. So what it is, it's the sum of the component-wise products. The sum of the products of corresponding, I'll say. Okay. So it's actually pretty easy to calculate, relatively easy, compared to the cross product, which we'll be doing next lecture. Some properties of the dot product. The first property would be that the dot product of a vector with itself is going to be the magnitude of the vector squared. And you can prove that just by kind of working out the numbers. I won't do that right here, but it's easy to do. Also that the dot product is commutative, so A dot B is equal to B dot A. Thirdly, the dot product is a distributive, so the dot product of A dot B plus C is A dot B plus A dot C. Fourth property would be that it's associative with scalar multiplication. So if you have a scalar times a vector A, dot that with a vector B, this is the same as if you had the scalar times the dot product of A and B. And fifth property then is the dot product of the zero vector and any other vector is the zero vector. Okay, so these are pretty useful. These can be handy, especially when you're trying to prove things. They'll be handy for some applications that we'll see later on. It's good to know about these properties of dot products. As maybe it's worthwhile to just do a simple little example of a dot product. The dot product of the vectors 2, -2, and 7 dotted with the vector 1, 0, 9. This is going to be 1 times, let me put it in the right order. It's 2 times 1 plus -2 times 0 plus 7 times 9. So this is going to be 2 plus 0 plus 63, so that comes out to be 65. So the dot product is a scalar. Always gives you a scalar as your answer. The dot product does not give you a vector. The dot product is a scalar. We're going to have the dot product has some very useful interpretations, and we'll see those shortly. First, it's related, this is the theorem. So the theorem is that if theta is the angle between vectors A and B, then we have this relationship. A dot B, this dot product, is equal to the magnitude of A times the magnitude of B, those are just scalars, times the cosine of the angle between them. And this can be proved using the law of cosines. So if we let's see a nice way of illustrating this proof. So I'm going to illustrate a little triangle here with sides C, A, and B. So the points would be, this is the point C, that's the point B, and this is the point A. Okay, so the law of cosines says that C squared equals A squared plus B squared minus 2AB times the cosine of angle C. This is the law of cosines relating to angle C. I can write this in if I write the vector AB is like the vector C, and the vector AC is the vector B. The vector BC is the vector A. So if I could, given these coordinate points, I could instead of talking about like the length of the side of the triangle is A, say the magnitude of the vector from B to C has magnitude A. So I'm going to write, so C is the length from A to B. It's also the magnitude of vector C. And this is the magnitude of vector A plus the magnitude of vector B, right? Minus 2 times the magnitude of vector A, magnitude of vector B, times the cosine of angle C. Actually, what I'm going to do is I'm going to call this angle theta. And so I'm actually going to change that C to the theta. Here. AB is the same as AC minus BC. That's something that we want to identify, because so the vector AB, right, is going from A to B, and to go from A to B, you'd have to go from A to C and then from C to B. The vector going from C to B is just the opposite of BC. So this is like saying the vector C is the vector B minus the vector A. Okay, so I'm going to write that here as B minus A on this side, dot with B minus A, that's the left-hand side, is equal to A dot A plus B dot B minus 2 times the magnitude of A times the magnitude of B times the cosine of theta. So I've used the second property from the previous slide, that the magnitude of a vector squared is just the vector dotted with itself. And C, the vector C, is B minus A, vector B minus vector A. Now I'm going to distribute the left-hand side, and we'll see what this comes out to be. So on the left-hand side, first I'm going to distribute this to the two vectors. So we'll have B minus A dot with B minus B minus A dot A. That's the way that I'm distributing it first, and then I'm going to distribute now this way to give us B dot B minus A dot B, and then we have minus B dot A, and then we've got minus a minus, which would be a plus A dot A. And this is equal to the other side, which I'm just going to copy. I'm gonna have to move some stuff over a little bit. Okay, because at this point now, I'm gonna cancel a few things. Okay, so because we've got b, that dot didn't translate. B dot b, b dot b, those cancel. We've got a dot a and a dot a. Those are, oh, you know what, a minus sign didn't move over correctly. That's not meant to be there. Let me just, that wasn't meant to be there. I think I copied part of the equal sign over. Those are going to cancel. And also, I want to just remind you that that a dot b is the same as b dot a, right? And so what we've got is, on the left-hand side, we've got 2 a dot b, actually minus 2 times a dot b equals minus 2 magnitude a magnitude b cosine angle. And if we cancel if we divide both sides by -2, what you're left with is the theorem that we have above, the results of the theorem. So what is this saying? The dot product of vector A and vector B is going to be the product of the magnitudes, the two magnitudes, times the angle between, the cosine of the angle between them. And the angle between them could be anywhere from 0 degrees to 180 degrees, not inclusive, right? The cosine, remember what the cosine looks like, right? The cosine looks like sorry, the cosine, I'm sorry, I thought I confused myself into being wrong for a second, but I'm okay. This is 90 degrees, this would be 180 degrees. So the cosine between two angles, the cosine of an angle, right? It's at most 1, and at 0 it's equal to 1. Let's just fix the mistakes I'm making. That's happening there. This is a very rough sketch. Really, we're concerned with angles between, say, 0 and 90, mostly what's going on. So the cosine is going to be 1 when the angle is 0. And so as theta is close to 0, or goes to 0, the dot product A, B gets bigger. And you notice that if you have A dot A, if you put it in the formula, this is going to be the magnitude of A times the magnitude of A times the cosine of 0, because the angle between A and A is 0, which is just the magnitude of A squared. Let's calculate a dot product or an angle between two vectors now, using the definition, or this theorem. So let's find the angle, the theta, between angle 2 to -1 and 5 minus 3, 2. So we need to find the magnitude of the two vectors. Let's call this vector A, and this is vector B. Magnitude of A is going to be the square root of 4 plus 4 plus 1. That's the first component squared oh, I'm on eraser mode. Oh, that's nice. b is the square root of 25 plus 9 plus 4. So it's the square root of the sum of the squared components, right? That's the magnitude of A, magnitude of V. So this is going to be square root of 9, and this is the square root of, I think this is a nice number. Is it nice? 25 plus 9 plus 4. That's 9 plus 13, 3, 8, 38. So the theorem tells us that A dot B is equal to magnitude A times magnitude B times the cosine of theta. Well, the dot product of the two vectors, A dot B, if we're going to calculate using the definition of a dot product, it's going to be 2 times 5, right, plus 2 times negative 3 plus a minus 1 times 2. This is 10 minus 6 minus 2. So 10 minus 6 minus 2, that comes out to 2. 2 equals 3 times the square root of 38 times the cosine of theta. So the cosine of theta is going to be 2 over 3 root 38. So theta is going to be the cos inverse of 2 over 3 root 38. Comes out to 83.79 degrees. So you can find the angle between two vectors by using this theorem. It also you notice that with the value of the cosine is 0 when you have a 90-degree angle. So this actually leads to a kind of a corollary of the theorem, which is if theta is the angle between vectors A and B, oh, you know what? Let me give this is just what we had. The cosine of theta is the dot product divided by the magnitudes A, B. And A and B are orthogonal, also known as perpendicular. If and only if A dot B equals 0. So two corollaries actually that we have from this theorem. Now often this is going to be important because we're interested in finding right angles in a lot of cases. For example, we want to we'll be seeing in just a moment that we're going to be projecting one vector onto another vector, or if we were going to be projecting some projecting a point onto one of the XY planes, and a right angle is involved, and so a dot product of 0 is going to be one of these essential aspects of such a exercise. So orthogonal vectors always have a dot product equal to 0, and that's going to be a this is going to be a big one. I'll put 2 stars and 2 exclamation marks. Okay. Now we're going to talk about projections. I haven't really defined projection, although we talked about projections a little bit in the first lecture, projecting a point onto the xy plane, for example. I just mentioned that. So I'm going to illustrate it with a couple of vectors. This is vector B and vector A. I'm going to draw them having the same initial point. So A and B have the same initial point. Okay. And B is not a 0 vector. So if we were to look at the vector that results from, basically, if we take it's kind of like the shadow of vector B, orthogonal to vector A, like we're shining some light in this direction at high noon, like think of a sundial kind of. The shadow that you get is going to be the projection. So I'll write it here. This is this vector that we have right here is the projection of B onto A. That's what's written. I'm going to put it in other words. The orthogonal projection of B onto the line containing A. Is called the vector projection. Vector projection of B onto A. Okay. I just want to make sure we caught this this notation down, because it's easy to swap the two. B onto A. A is down below, so that's why it's like it's down there. A is like below B. Now the scalar projection of B onto A is the signed magnitude. Ooh. Just had a bit of a power issue. The signed magnitude of the vector projection. And is B cos theta. All right. Now here it's pretty clear to see that that is the case if you just look at this triangle that I've formed. The length of the the projection, the vector projection, is going to be magnitude b cos theta. Because if you were to create a triangle with this side of length magnitude b and this theta and this a right angle, then this side is going to be magnitude b cos theta, and this is going to be magnitude b sine theta. This is just going back to trig identities and all of that. And so if this is the vector b, this whole thing is the vector a. So what I've written is the length, like the length of it is magnitude b. The length there is magnitude b cosine theta. We can kind of rewrite the projection using other notation. So as we had before, a dot b, this is the theorem from above, a dot b is magnitude a times magnitude b times the cosine of theta. And we can, this magnitude b cosine theta is the projection of, this is projection of, I should say, let me take a step back. Okay, so let's taking this, we can rewrite things as we can take the magnitude of b is equal to this is just dividing both sides by the magnitude of a, right? A dot b over magnitude a. Now the left-hand side is the scalar projection of, this is the scalar projection of this is the scalar projection of b onto a. So to the projection, the vector projection of b onto a is going to be the scalar projection of b onto a times the unit vector of a. So you take a and divide a by its magnitude. So this is a way of getting the vector projection. You take a, you divide it by its magnitude, it becomes a unit vector. You multiply that by the scalar projection, which is a scalar that tells you how long to scale this vector. And we can do a few substitutions. We can write a dot b over magnitude a on the and then well, it's times. It's just a scalar. I guess this is it's a dot. Well, it's a scalar product, so I don't have to put a dot there. But we have a over magnitude a. The denominators are both scalars, so I can write this as a dot b over magnitude a squared times a. So here's a formula that we can use to get the vector projection of b onto a. So given a vector b and a, we can find the kind of the shadow that vector b makes on a by following this formula. Maybe you want to see an example of this. Let's just do an example. Let's find the vector projection of B onto A, where A is the vector. Let's use the same vectors that we did in an earlier example. 2, 2, and -1, and B is 5, -3, and 2. Okay, so as I said in the formula, what we need is A dot B, which is 2 times 5 is 10, plus 2 times -3 is -6, plus -1 times 2 is -2. So that's 2. We had that from before. The magnitude of A is in fact 2 to -1. That's square root of 4 plus 4 plus 1. It ends up being a 3. So the projection, the vector projection of vector B onto A, it's going to be the dot product, it's A dot B, which is 2, over a magnitude of A squared, which is 3 squared, times the vector A, which is the vector 2, 2, -1. So that's 2/9. I'll distribute that, so we have 2 times 2, that's 4/9. Then we have another 4/9, and then we have -2/9. And that's how you do a vector projection. Okay, that's it for dot products, for the foundational stuff for dot products. We'll do more practice together.